Yeah, so I'm Nico Hauwert, Program Manager for the Austin Water Balcones Canyonland Preserves, and I've been passionate about forests and caves since the 1970s. And so we'll be talking some about climate change today, the local effects, how you can impact the climate and water and caves and springs, and some historical perspective. So a lot of times we'll go back in history and look at things, and we'll look across the world too. So we'd like to think that as a scientist, we're like the apex of evolution and we know everything. You'll see that a lot of stuff was discovered a long time ago that we'll talk about. So that's what I'm going to be talking about today. Jam-packed, climate change, caves, effect on the environment. And so this is an illustration here of Austin and the underground world below it and all the urbanization on top. So can you all see the whole screen? I can't. I have to hide the screen to see it now. So one thing we'll start off with on the first part is we'll have a worldwide view of deforestation and the patterns, and a lot of the repeated patterns we had here in Texas. So this is showing you maps of virgin forests in the United States. According to this researcher from 95, back in 1620, 1850, and 1920, and you can see across the United States how the virgin forests were much less in 1920, and certainly by today than they were in 1620. So I want to show you that. So across the world, it's been noted that people have been doing deforestation, particularly over the last 8,000 years, and they cut trees for construction, fuel, particularly livestock grazing. They create fires, which are mostly all anthropogenic, caused by people. And they'll change their environment by draining the wetlands. I came from Houston, where I saw this happen a lot with the bayous there. Directing their irrigation waters, enhancing agricultural production. And so if you remove a lot of the trees and you start losing the soils, then you don't have, you can't regenerate forests at some point when the soils are all gone. Now in our area, the ash junipers we'll talk about are really good about regenerating soils with their duff material. And as a result, you get this transformation across the world where you not only destroyed habitat for a lot of the wildlife, but then you have a drier landscape that's more prone to wildfire and less water available for people. So in recent millennium, humans have become the primary cause of increasing numbers of ecosystems being kept at early stages of successional sequence. What that means, forest sequestration. They take us back to grasslands and things like that. So one way you can pick this up, across the world in history, is looking at sediment cores. And you can see that a lot of the sediment deposition happened at times where people disturb the landscape. And then you can detect this downstream in the streams, like the Now River Valley. Once people started deforesting the upper areas, they could see that in the sediment cores later on. So back in 360 BC, we're going to go back to Greece and look at an example of that pattern. Plato wrote that Greece, by 360 BC had become basically a wasted body. He said they cleared the forests. After the forests were gone, the soil eroded away, the rainfall diminished, spring stopped flowing. Then they started having really bad droughts. They had droughts and then floods as well. And so these are locally derived changes. These aren't worldwide climate changes. Not to discount, that the carbon in the atmosphere and the greenhouse gases certainly do have an effect on global climate change. But the point I'm making is there are also local changes to your environment through deforestation being one of them. So the Greek landscape, historically covered with evergreen oaks, pines, cypress trees, cedars, laurel, carob, wild olives, deforested for firewood to make charcoal. the lumber to build things. And then wildfires were accidentally sent that burned a lot of areas. And sometimes they did it intentionally as a military operation. And then, of course, to make the landscape suitable for livestock, you had to clear the forests. And so as a result of that, nowadays in Greece, let me go to nowadays. Here we go. Okay, so like many places across the world, in Lebanon has the same problem. Australia on the western side, after you had a successive deforestation, you lost the soil. They see diminishing rainfall, a conversion from forest to kind of a maquis shrub vegetation, which is a lot drier, or grasslands, and then the countrywide wildfire risk is increasing, like we've been seeing in Greece in recent years. And you can't grow the forest again now very easily because the soils are gone, so there's no nutrient source and water source for the trees to grow. So in 2007, it was declared a state of emergency in Greece. You had fires burning across the whole countryside. And we hope that Texas never becomes like this, is the point. I'm going to try to move this thing up. Y'all can't see the very top of this, I bet. So let me see if I can move this down to here, maybe. Okay, so there's some cases where deforestation and soil loss was attributed to cause climate change, and one of them is in Africa, Ethiopia. One study note that 2.9 million years ago, there was about 65% trees, 35% grass, and then 2 million years ago, you start seeing human artifacts in Ethiopia, and the landscape changed to about 50% grass, and you had less precipitation. And the monsoons that would normally come to Ethiopia stopped coming. Right in 2017, related the increasing human population, the spread of domesticated livestock in the Sahara region, used to be forested. They started burning the landscape, and it caused a transformation from forest to shrublands, and then the soil erosion, which could be detected in the Nile River Valley at the mouth. Occurring during this time. When you carbon date it, you can see that it was caused during this time. And so the deforestation caused localized warming, resulting in climate change. The monsoon rains don't come there anymore from the Mediterranean. And so it turned into a desert at that time. So the Sahara Desert used to be forested. This researcher attributes it to the man-made climate change in the area that caused it. All right. So Central Texas, what were the changes and why did they do this? And we'll look at a little bit of science behind that. So on the left-hand side, you've got the ecological regions of Texas. This is a map from Lisa O'Donnell, who did a report about the deforestation in Texas and how this used to be a forested region in the Edwards Plateau with prairies interspersed in here, but a lot of it. And the conception we have, like if you see Tom Hanks' News of the World and you see it portrayed as a prairie, a lot of that, when she looked in history, was people were actually talking about the Blackland prairies and the Gulf coastal prairies, which some of them were very large prairie areas by that ecological region. The Blackland prairies in our area are on basically the east side of I-35. And so whenever you looked in history and they talked about all these prairies, they were talking about the east of I-35, according to Lisa O'Donnell's research here. And on the right-hand side, you could see some maps of the area from 1940, what Texas kind of looked like in 1940 during that time. And north of Austin, they did have immense herds of buffalo, on the in the Waco area. And here's this is Buckley, who did a geological assessment of Texas in all of its resources back in 1874. And he's basically relating here. He said that he saw cedar trees, which are ash juniper, common in Austin, they're cutting it for fencing, posts, rails, railroad ties. He said he's seen some that are 100 feet tall, and he had a lot of stories about ones that are 100 feet tall and 3 foot in diameter. Many of these were from red cedars from East Texas, but they were very large ash junipers at the time. And on the right-hand side, you can see some illustrations from 1904 from William Bray. One of them is showing this Cuernavaca Creek, all the forested area, which is still looks a lot like that. It hasn't really changed. But then this other hillside, the other side of the hill, which is a tributary of Barton Creek, and he talks about how they cleared it and how you're losing all the soil, and how the storms, storm floodwaters are becoming worse as a result. This was William Bray's observation here in Austin in 1904. So what William Bray talked about in 1904, he said that the trees serve a really useful purpose. Their deeper roots increase the infiltration so the water can go in the ground. That reduces the runoff for floods and reduces the erosion because the trees are holding back the soil. And when you clear cut the forest, you're increasing the erosion, increasing flooding, and that the forest and soil together act as a huge water reservoir for water, holding the water, releasing it, when you really need it during the droughts. And he was aware there's a hypothesis. People believed even at that time for hundreds of years that forests actually drew the rainfall, and he didn't know the evidence for that. And he said people were probably confused because there's a lot of moisture associated with trees. All right, so here's some more information. This is from Elizabeth McGreevy, had this in her new book. And if you haven't gotten it yet, you might be interested in seeing her book about ash junipers and the history of deforestation here in Central Texas. And apparently that when the map on the right-hand side shows you, this is from 1899 from Robert Hill, and you can see the train tracks going right now to Llano area from Austin area. And so they were using that to ship in cattle, and they were shipping out lots of ash juniper, which was a valuable commodity. Even in the Northeast, they used it here for all kind of purposes, for charcoal, for building stuff, for railroad ties. And Elizabeth McGreevy also found out that they were shipping it to the Northeast. A single train would have 40,000 posts of ash juniper. And in 1873 and 1874, they were shipping 200,000 ash juniper logs to the East Coast. And that's not even what they're using here. That's what they're shipping off. So they're using quite a bit of it. It was a valuable commodity for our area at that time. And then there's a geological survey written in 1912 of the Llano area. And he's basically saying that, they're clearing the cedars across the area here in the Llano area for the Llano River. And as a result, we're seeing a lot of sedimentation in the creek in the Llano River. So back in 2018, when we had flooding and we had really turbid waters come into the Austin area and plugging our water filters, you can relate back to 1912 when he said that they're clearing the trees. It's causing the sedimentation of the Llano River. So let's get some into caves. These are some of the South Austin caves. Natural feature of this area, and of course they were back then. Both of these particular caves, you can see the entrances look like little skylight entrances, and they're kind of underhanging. And so these are collapsed caves, which means they were formed at the water table a long time ago, and then the ground surface cut down 200 feet to where there's a shallow veneer of a roof, and eventually they pop open, and there are collapsed caves all over the Austin area. There are thousands of them I've seen. I have never seen one in my lifetime that recently popped open, that wasn't caused by people. We'll talk a little bit about that. Caves also are very important for our heritage for cave ecosystems. The bats you see in bridges, attics, the first city hall and stadiums, where they used to live in caves, but the caves have been all filled up, and this is why they live a lot in urban structures nowadays. The program I manage is the the endangered species permit for endangered karst invertebrates and also songbirds, the golden cheek warblers. And we also have a federal permit for protection of the Barton Springs salamander, which also lives underground in the aquifer. And there's a little bitty monster there, that little pseudoscorpion is what that is. So caves are also really important for recording history. And a lot of the ancient Pleistocene mammals that used to live in the area in central Texas, including stuff from Africa, like camels and lions and hyenas, you know, used to live in Texas 10,000 years ago. And their remains can be found in caves like the saber-toothed tiger remains in Friesland Cave on the upper right-hand side. Just to point that out, this is what a sinkhole looks like. Sinkholes are like skylight entrances in the caves, but I showed you before collapsed sinkholes, and these are solution sinkholes, so they can also be formed by the dissolution of the surface, and usually those tend to look like bowls. The bigger the area that's captured by the solution sinkhole, the bigger the bowl is. Okay, now catastrophic collapse sinkholes. When you think about sinkholes, most people think about this. Every case I've ever looked at has always been as a result of people that cause that sinkhole to suddenly catastrophically open. They don't kind of randomly do that, at least not often. Over a few thousand years they do. So the main causes of these are things like if you have, like you're in a swimming pool, you weigh less water as does rock, you know, that has this buoyant support of water. So if you pump the water table down, suddenly that rock might be unstable and cause sinkholes to open up. Places like Florida, where the water table is really shallow, or gold mines in South Africa, this happens a lot. You can pump enough water out of the subsurface as the rock is really soluble, like it's made of salt or gypsum. In places like New Mexico, you can form huge sinkholes just by pumping up enough water. The water typically is used for fracking, and so they pump a ton of it out, and it actually makes a cave that can create a sinkhole hundreds of feet in diameter, couple hundred feet deep. You know, so that's one of the causes. If you leak enough water through leaking water lines and wastewater lines, these can enhance the dissolution of the rock and cause a sinkhole to form. Or if you put a really heavy object over a shallow roof, or it's a really big cave, the bigger the cave, the bigger the stress field generated at the surface. We don't see this in our area very much because the water table is really deep. But if you put a heavy object, a water quality pond or a building on a cave, yeah, those can cause a sinkhole to collapse in the area. These are all anthropogenic catastrophic collapse sinkholes. And one natural feature in our area are swallets, and these were noted in the 1890s here in this area. There were caves in the creek bottom, and sometimes you can see whirlpools. I can a lot of times hear them kind of, you know, and so I know they're around and I start looking for them. Sometimes you can see the whole creek going underground, and these are called swallets, where you have a lot of water going in the ground in the creek. Here's the effect of me plugging one of those sinkholes at the bottom there with a couple other people. Back in 2003, one day we were unplugging it, and the creek was flowing. And what happened then is these are if you take the gauging flow stations that are 20 miles apart, and you take the data from them, and you can see that the result of me unplugging that sinkhole caused the creek flow downstream to diminish by 33 cubic feet per second. Okay, but some people say, well, that's kind of small potatoes compared to floodwaters of 20,000 cubic feet per second, you know. And so part of the point I'm going to make is that upland features have a really important role too in reducing floodwaters. But then again, you have this thing happening. You have plugging of swallets at a wide, many places across the area. Here's another case here. Historically, in the 1890s, this is the Blanco River in both of them actually, but on the upper left-hand side is the Blanco River at the mouth of Halifax Creek. And Peter Sprouse found some historical data that indicated that that they had a place here where the entire river, the Blanco, would go underground in this cave. And the problem in the 1890s is they had a mill in the Kyle area that they wanted water going to turn. And so they made a point to plug this feature. And this is a place, by the way, where I could hear swallowets going on. And so we found a place where the water was going down. I put some dye in here. It showed up in Barton Springs 3 months later. Now, the effect of the widespread plugging of features across the area, you wonder how that has contributed to flooding like you're seeing in the Blanco River and other places. So here's just a basic kind of illustration of karst areas like we have in the Central Austin area. On the Edwards Aquifer, we have these bowl sinkholes, you know, feeding water down or caves down to basically highways of flow in the groundwater. Few highways of flow where the water goes really fast along there. But the water traveling in between there is not going through little pores, actually. It's going through smaller cavities. I see a little conceptual model of what the water table was like in this area. So one of the reasons they filled caves in the early days is they had, I would say it's almost like a superstition that caves produced bad air. And miasma was a term used around that time. They believed that a lot of illnesses were airborne from rotting vegetation. So around the 1850s in England, in London, they had a cholera epidemic. People were dying. They attributed it to the bad air. One doctor, Snowden, tried to explain to them that all these people are drinking water from the same well. I think it's the well that did it. And they said, no. We're experts. We know it's the miasma that's causing this. So there was a thought at that time that bad air is making people sick. And so in this particular case here in 1885, they're relating that a whole ranger camp was abandoned because there were caves nearby. And they were worried about the bad air coming out of the caves. Also, Vinther and Jackson talked about in Williamson County, many people routinely sealed off clothes to eliminate hiding places for varmints and predators. You know, predators probably on livestock at the time. So in the late 1890s, you know, the Hill and Vaughn, they thought that the aquifers like the Edwards Aquifer were dominated by caves because they could see caves on the bluffs. They saw aquatic salamanders in wells back in the 1890s. And they reasoned that, no, these salamanders aren't just living in isolated pockets. You know, they're actually caves connecting really well in the ground. They could see the swallowets in the creeks where all the creek flow loss was going underground. So they had a pretty good idea back in the 1890s about water flow in the aquifer. Since then, in the last 200 years, you know, a lot of caves have been filled. And so when I'm on a site assessing it, maybe for a new preserve, I see these and these scream to me as caves. This is a cave filled with rocks. Ranchers would fill them to keep livestock from falling down pits. This is a cave full of trash. Every ranch had their dump site where they dumped the trash in. Here's some more. This is on the Dahlstrom Ranch, big sinkhole. You know, fortunately, the family in this case always intended it to be, you know, preserve land. So they shared this to me about what they did with the sinkholes, and here's our trash dumps and stuff. So that was kind of cool. But every ranch did this. It's not weird ranchers. If I evaluating a ranch, I wonder where are their trash dumps, because there's a sinkhole or cave nearby where they would dump their trash. So this is what we look for. This is Circle C Midnight Cave in Circle C Slaughter Creek, and this is what it looked like. I took this picture in 1993 when we went down there. 20-foot thick of trash. One of the trash dumps for Covert Ranch, which was later called Circle C Ranch. And then we cleaned it out. Mark Sanders was the main guy. Mark Sanders was Parks and Recreation. He was the main lead on cleaning this out. Now he works for me in the BCP, but now it's all cleaned out. We didn't even know there's a pool of water at the bottom at the time. So every ranch, they has about 3 or 4 sinkholes. They plug the bottom of it. made them into stock ponds. This was Dahlstrom Ranch again, where the rancher could say, yeah, here's the concrete plug that we plugged it in. And there was a hunter there one time a couple of years ago who heard this big sound during a rain event, and suddenly the plug on the sinkhole opened up, the stock pond. And so it didn't work as a stock pond so well anymore because it was leaking now. But every ranch has these large sinkholes that are stock ponds, converted to stock ponds. And then later, many of these were converted to water quality ponds. Here's one on the Costco Mall there at William Cannon and Mopac. I was doing some dye tracing at 5 o'clock in the morning. I was driving over, this pond had been leaking for a year since they built the shopping mall. But I was driving over and I saw the pond was empty at 5 in the morning. And sure enough, 12 foot of water in that pond caused it to blow out. As I described to you, the catastrophic collapse sinkholes. This is one case in Austin that happened in South Austin, 2012. So another important feature is some of these really big solution sinkholes start taking in whole drainages. Some of these are 50, 60, 100 acres in area that are just going down into a drain. And if they're working properly, they don't even, the water doesn't even end up to the creek. It goes into the aquifer. And this is a good thing. So this particular sinkhole on the Dahlstrom Ranch, this is how we found it when we were doing assessment for the, if we could acquire it for a preserve, and then we pulled all the dirt out, and it looks like the one on the bottom now. And Hannah Colford took this picture of the water flowing into it from the Hill Country Conservancy. Now I mapped about across the Edwards Aquifer that about 10% of the whole area is internal drainage. It goes into one of these sinkholes. A smaller amount goes into quarries, which also acts as an artificial one. And so, but the actual amount, because there probably were a lot more than I know about, there might be maybe 50% of the recharge area at one time used to be internal drainage. So what's the effect of when you plug these? You, like say in Tony Berger Center and Highway 290, where they divert the flow that used to go in a large acre sinkhole, and now they drain it to the creek, drain it back to the creek, or they plug this sinkhole and it just goes to the creek on its own. So what is the effect on that on a big scale? Obviously, it's increased our flooding problems. So one thing we do, this is on the William Russell Carse Preserve. Picture of the sinkhole, 2012, it was plugged up, and then they have this crew cleaning it out, restoring it. Now it takes all the water that goes to it into it. And so this is how we restore them. So come the 1980s, when they started developing a lot of the recharge zone, they had this kind of radical new view of the recharge zone, as opposed to what Robert Hill thought in the 1890s about it being cave derived. They thought, well, these aquifers are really, they're going through small pores. So if you're going from, Highway 45 Southwest, it'll take 3 years to get to Barton Springs. If you're coming from Onion Creek, it's going to take 5 years, because we as mature scientists all know that water goes through little pores in the rock, and not through these caves that are, we don't even see many of those caves. So there couldn't be that many of them out there to begin with. Then around the 1980s, I worked for the Barton Springs Water District, and we started seeing some of the wells, Rolling Wood area, Shady Hollow, Sunset Valley, their wells were starting to get contaminated. And a lot of those started going on to other sources of water because they couldn't use their well water anymore. And also during that time in the 1980s, a lot of people forget this, but like in the Shady Hollow area, when they built it, the water used to go naturally into sinkholes, these large internal drainage basins. So when they built the subdivision, they just kept doing that. They kept diverting the runoff from the urban areas into the sinkholes in Rolling Wood, Westlake, Shady Hollow. And then they started trying this thing where they would treat wastewater for some subdivisions like Shady Hollow, Travis Country, down to some extent, and they irrigated over the Edwards Aquifer. Because all the mature scientists know that the aquifer treats the water really well. So this is really widely thought during the 1990s. Also during that time, people started, the wells became unpotable around that time, and there were frequent petroleum pipeline ruptures on the big scale that would happen across the area, but there wasn't much monitoring to see what the effects of those were in the ground. So then we had these pathogenic outbreaks in the 1980s, and a lot of people forget that in Georgetown, 1980, 8,000 people were sick from enteroviruses from their well at that time. Now, the well operator named Ernest Robles, he told me, he said, we think that probably what's causing this is there's a golf course nearby where they're irrigating wastewater. But actually, before a cause was officially determined by this task force, the governor disbanded the task force, he said, and we never really came to figure out why. But it just went away. Whatever it caused, it didn't happen again. In 1984, the wastewater system of the Bronze Station contaminated their well water, and about 2,000 people got sick in San Antonio. And then in 1998, in Brushy Creek, a City of Austin lift station overspilled into Brushy Creek, and there were a lot of water wells nearby, and about 1,500 people got sick from that pathogenic outbreak. So in the 1990s, we started groundwater tracing the aquifer for the first time, and that kind of dispelled that myth about water moving slowly through the aquifer. In the Highway 45 area, which is shown in Slaughter Creek on this diagram, they expected 3 years to Barton Springs, and it took every trace I've done in this area. I've done about 5 more in this area, more than what's shown here. Every green dot is a place I put a dye, by the way, to trace these red flow paths, which are the few really major groundwater flow paths. But even in between the green dots, they all got to Barton Springs fairly quick. Instead of 3 years, from Highway 45 Slaughter Creek area and Bear Creek, all of them pretty much took 2 to 5 days to get there. So instead of 3 years, that's a few days. Onion Creek, which they estimated 5 years, we had tracers getting there in 2 days to Barton Springs. During the drought, things kind of slowed down some, and sometimes it would take 3 weeks to get from Onion Creek, which is still quite a bit faster than 5 years. And so we learned also some things about the flow paths. We learned that the Blanco River is actually what sustains Barton Springs during the drought. And we also learned that Barton Creek really isn't the main source of water for Barton Springs, but primarily it feeds Cold Springs on the Colorado River, which is a major spring. It flows, it's been measured to flow in the, before the dams were built, about a third to half of Barton Springs flow. So it's a pretty major spring. And this, even downstream of Loop 360, the water will kind of split between Cold Springs and Barton Springs where it goes to. And here's about Blanco River. So in addition to tracing directly from the Blanco River to Barton Springs, taking about 3 months, here's an analysis of showing you the Barton Springs flow in blue, how during a drought it kind of goes down like really fast. And then during a drought, it reaches the same level of what the Blanco River is recharging at Wimberley. And the Blanco River here never really dried, at Wimberley. It's always continuously flowing, which explains why Barton Springs never stopped flowing. Onion Creek, while on the other hand, is the biggest source of recharge overall for Barton Springs, but during the drought, you can see here it's dry for over a year, and producing very little of the flow that could be attributed to Barton Springs. And so here's an example of a tracer I put in Bear Creek, just upstream of before they put in Highway 45. And it was flowing all the way to about Highway 45. I put 5 pounds, which is just like a handful of dye. There was no swallets in the creek I could see. It was all gravel covered bottom. And we put 5 pounds in Bear Creek. And then you could see that these dots are representing the peak, the concentration showing up in Barton Springs within 2 days, and then mostly coming out in 5 days. So within 2 to 5 days, it's kind of brushed out. We measured that about half of that dye showed up at Barton Springs within those 5 days, 45% of the dye. And that was 12 miles away that we injected the dye. So water's moving really fast. This also explains to you that the aquifer really doesn't treat very well. And this is an example of an organic dye, which tends to stick on stuff. And so even though it was sticky stuff and we put it in gravel bottom creek, we still saw half of it showing up in Barton Springs about 5 days later. So things about bats, I mentioned a little bit about how there used to be a pariah in Austin. Merlin Tuttle came here and showed people that, you don't have to keep killing bats because they're really good for you, So now it's the mascot of Austin. Part of the reason that bats have a potential to transmit diseases to people is, of course, when you fill in their habitat, they're forced to live in urban areas like they do now. But we've never seen a case that I know of in rabies in the Austin area, although that was a big fear back in the old days. This is another reason why people would fill in caves, just because they were freaked out about bats. And now that at the Wildflower Center, we've been filling caves there, bats are coming back. It's hard to predict when they're going to come back. A lot of times on the caves we open up, but frequently they do. And so what I'm going to go in next is some of the relations between local deforestation, how that affects the climate in the area. So there's other things that can affect the climate. A lot of these are anthropogenic, but some of them are not. Changes in solar radiation, then the increasing greenhouse gas effects, the heating of the Pacific waters, which is the El Nino, La Nina weather cycles that we're familiar with. A volcano can cause, short term can cause cooling, but long term it can cause the heating and melting of ice across the world. In history, things like geomagnetic field reversals, meteor impacts, all these things can affect the climate. But we're not going to talk about these. We're going to talk about primarily deforestation and the effects of that on it. So where you have vegetation in soils, you have the potential for infiltration and absorption and storage. Like William Bray talked about how the soil is like this natural functioning reservoir that's available. But once you have compaction and you lose your soils, usually because you cleared your forests, then you can have a lot of runoff. You can have worse flooding, and then you evaporate water a lot faster. So when you come around to a drought time, the water's already gone, because there wasn't much storage to begin with. Sure, to evaporate in the environment, that's not necessarily a bad thing. We'll talk about that. But you kind of want it to stick around for a while. You want the water to stay around for a while and not lose it all to the environment quickly. Of course, there's impervious cover, and you're all aware of this. Once you put an impervious cover down, increases the flooding, the creek erosion, degrades the water quality, doesn't have as good chance to filter as it does through vegetation. If there were springs in the area, they can dry up or they get replaced with urban runoff. It might be now a water line leaking that's feeding that spring, or wastewater line leaking that could be causing that spring to flow now. And we build water quality structures to some extent to kind of reduce the effects of the impervious cover, temporarily store the water, kind of artificially, like the soil would do naturally. So it's been pretty well studied that forests diminish the runoff. And these are some of the studies. It's pretty well documented that when you have forests, the roots increase the infiltration of the ground, and the litter helps to store the water in the area. Some people look at it bad. They say, well, they're taking the yield from the creek. And I guess you can look at that as impervious cover doing the same thing. But really, when you look at it, it's good to infiltrate water in the ground. It's not stealing water from the creeks. Most of our base flow is fueled by springs and not the runoff that happens around rain events. So here's some studies that show that the roots are enhancing the soil infiltration. Adrian Lindley used this big pan that you're seeing on the top there. He used a water truck to fill it with water, and he tests different kind of landscape environments and see with sinkholes, you know, if they were soil filled is what he primarily was testing. But the biggest infiltration he saw was actually where there were juniper roots. And that's where, in the Trinity Aquifer, that's where we saw most infiltration, actually. So one of the first studies in the area to really study the water balance was one that I did around 2002, South Austin, just south of the Wildfire Center, where I put up a climate tower to measure the evapotranspiration. Of course, we had rain gauges, soil moisture probes, meters to measure the radiation from the sun. And this device on the bottom left is called a flume that measures the flow going down the creek, which in this case all went into a sinkhole. It's a big internal drainage basin sinkhole, which is shown in the wooded area on the top left. Is where this cave is. It's taken all the water from this whole 50-acre area. And if the sinkhole wasn't there, that water would flow to the creek, and it helps me give an idea what would happen to the runoff. So it represents runoff in my water balance. And here's what my climate tower looks like to measure evapotranspiration. It's like a 50-foot high tower where I can measure evaporation and transpiration together. So evaporation is the liquid water that changes to gas. And as a result of that, it causes cooling, which is a good thing to cool it off. Transpiration is where the plants use water. And I guess loss might be a bad term here because they're using the water. They're making cooling. They're taking nutrients from the soil. And they're also taking in carbon dioxide from the atmosphere. So they're helping to sequester the carbon and reducing the effect of climate change. So these are one of the ways you can directly measure evapotranspiration is with a tower like this. Over a mile area or a pretty large area, you can get an average representation of the evapotranspiration. Potential evaporation, a lot of times you'll hear that word used, and that's where you have like a pan of water and you have all the water available, say like in a lake, and you have no limit of water. Like in my area, the soil is going to get dry and then it won't produce as much water anymore, you know. But potential evaporation is where you irrigate crops or you have a lake, and so there's no lack of water and the water is always available to evaporate, and it's always going to be higher, usually about 25% higher in my area than what I actually measure with the tower. And so one of the things is that back in the 80s, when they had the concept about the slow flow through the aquifer, they also came up with this thought that only 1% of the rainfall recharged the Edwards Aquifer, which is kind of, actually, they came with less than 1%. And that's kind of like as if other places of the world, if that was a shale or a clay, you know, it's not, or a parking lot at Barton Creek Mall, perhaps. All over the world, nobody gets values that low, you know, but people who are building or doing wastewater irrigation love those values. And so that was, you know, people kind of all agreed that that was the right value until we actually measured it with a tower in this area more directly. And so when I actually measured, you know, all the components of rainfall, I found that actually 28% of the rainfall goes through the soil and in the cave in this area instead of the 1%. So that's a big difference, not 1%, but 28%, kind of like the groundwater tracing where they were estimating years and it takes days to get there. Big difference. So the soils are a whole lot more pervious than what they were estimating in the 1980s. I'll just kind of briefly, sorry about this. This is you know, I've got one value here on this graph at my headquarter flat sink site near the Wildfire Center. Like, what's the average amount of evaporation and transpiration of rainfall is what this is showing you. And then it's proportional to rainfall. So it's going to be different how much evaporation and transpiration you get. But other people across Texas also measured places that were wooded and places that are grassland. And I compiled all their data in relation to rainfall to kind of see what the pattern was. And so this is kind of what this is showing you, is that the line is representing what's the evaporation and transpiration percent of precipitation of rainfall. And then the remainder is basically what runs off and recharges. Normally the runoff is kind of small, it's only like 3%. So mostly that remainder is how much goes into the ground and infiltrates. And it's going to vary depending on whether it's wet or dry, period. And so during really drought periods, you see that the towers are showing you that in the grasslands, which are in this case, the triangles are the grasslands and the circles are the wooded areas, that they're losing more water, the grasslands, during the droughts than the forested areas. Now, during the really wet periods, the forests in general are using more water. And this has kind of been proven in other studies that trees, their stomata opens up. They take in water when the water is available. And during a drought, the ash junipers and other trees kind of cut back. So if you look at the balance of things during the drought, they're kind of saving on water, the trees, whereas the grasslands tend to lose more water to the environment through evaporation. And it may not be around when the drought comes really late in, so there may not be water available then. But the thing that trees are doing, they're using water during the wet periods, and that's good because that's hoping to reduce the floodwaters. So when people say trees are stealing water, all in all, they probably use more water because there's more water during the really wet periods. But that's actually a good thing that they're using that water. We'll look at other ways why that's good. So this is showing you kind of the difference that during the dry periods, there's higher evapotranspiration going to the environment and during the dry periods, they tend to get lost more in the grasslands and the forests. But that's not all consistent. Not all of these sites are consistent with each other. So they might be showing different things. It's helpful to have more data is the point here. Certainly could use more data. So the question next is a high evaporation transpiration bad? Is it bad that you're losing that water to the environment? And the answer is no, it's really not bad. In the process of evaporating and transpirating causes cooling. So if you like this to be cooler during the peak summer months, trees are good for that reason. It's not just the shade they're causing. You're in a car, you're in the shade, but it's still hot. They actually transfer the energy from the sun into cooling, and they sequester carbon at the same time. So during heavy rainfall conditions, the aquifer and tree storage reduces flooding downstream. Also, the evaporation and transpiration lost causes local rainfall. And it's estimated that 61% of the terrestrial rainfall is actually derived from the land surface, not necessarily in the rest of it's from the ocean. So most of it's actually terrestrial. Now, another study came up with 40% of rainfall originates from terrestrial, but it's a pretty high percent, about half of it. We'll talk about how the low pressure from rising vapor through the evaporation flux draws more rainfall in. So this is an old thought that forests draw rainfall. Maybe there's some truth to that. We'll talk about that a little bit. And if you end up with a hot, dry area like you are in a grassland prairie area, there are high pressure systems associated with that actually keep the rains from coming in. And we'll talk about some of the studies that show that in a minute. So the cooling effects of vegetation, as opposed to the heating of the ground surface, we'll show you some data on this. Here's some, particularly I want to show you the graph on the left-hand side, which is from Africa. And they did some temperature readings in the grasslands, woodlands, and forests. The forests are like more than 80% trees. And what you're seeing here is that you don't get as hot in the forest than if you do in the grassland. You're going to get a lot more higher temperatures in the grasslands there in Africa than you do. And that's shown in all these other studies as well. In fact, it's estimated worldwide that about 18% of the current global climate change is as a result of deforestation. It's causing the heating of the climate, not necessarily. And you are, of course, losing carbon as well at the same time, particularly if you're burning it. So that's also contributing to climate change. But just the simple fact that the ground surface is heating because you're having a grassland instead of a woodland is making things hotter. And this is intuitively obvious. If you've never been out in the woods in a hot summer day versus a prairie, you will feel the difference between the two. It's pretty intuitive. So we've been doing our own measurements last summer, not really the hottest summer of all, but over several months. Christina Campbell did some measurements. We have these little posts about 3 feet off the ground. We have temperature humidity probes. And here, over these several months last summer, this is the maximum daily temperature. At these 5 different sites, we're seeing about 9-10 degree difference in temperature between grasslands and woodlands. The woodlands are cooler than the grasslands invariably. So really no much question about that. They're causing the landscape to be cooler. So do forests attract rainfall? And several reasons that this happens. One thing is that the leaf area surfaces in forests, there's so much leaf area, it's so much more than the ocean surface, which is one plane. So you can actually lose more water in a forest than you can in an open ocean area. And this kind of explains to you why you might see more water coming from a terrestrial environment than in a Gulf of Mexico or an ocean. Also, the rising cool water from evapotranspiration creates a low pressure rising system that draws in the moist coastal wind currents. And Makariva and Gorshev in 2009 have been showing the physical basis behind this. In 1960, Namias explained that the droughts in Texas, don't correspond really to the warming of the Pacific Ocean like we think it is. A lot of times we say, is it a La Nina near or La Nina? He knew in 1960 that it's actually related to the soil moisture that's available at the time, which relates to whether you have forests there too to help keep them in. Now, if you've got rising warm winds, you have these anticyclones that are high pressure fronts, and we'll look more at that in just a minute. Also, the biological aerosols help to precipitate rainfall. Is another factor there of why forests cause it. So Makariva did this cool report, and she also, in addition to the physical basis of how forests produce rainfall, she did these cross sections across the world and said that it's not, whether it's forested or not, doesn't depend on how far from the ocean you are. And she did this example from North America, showing that North America has a lot more moisture far inland than East Asia, and distance-wise. And she attributes to the fact that North America still has more forest than Mongolia does, and therefore is the cause of more rainfall in the area. So Milian looked at that in the Mediterranean Greece area, and he attributed the terrestrial waters from the forests, the soil, and the lakes as a reason for what gives you the to have rain forming or not. And he attributed that to whether you're going to have droughts in the Mediterranean, is how much forest and soil is still remaining. He also attributed it to flooding in England and Europe, because he says that you get these built up fronts and they don't ever rain. They just kind of building up, then they break through, cause a huge flood to occur in Europe from the Mediterranean. So this is a kind of cool paper from Ellison. So something about that he relates here is what we've been talking about, is that the forest, the conversion of cooler temperatures, we're going to look at how that tends to take the heat off really extreme climate for one thing, but it also provides better retention for droughts, for the water during droughts, and reduces flooding, which is what Bray said back in 1904 and Plato before then. So have there ever been measured correlations between forest and rainfall? Here's a couple of studies. One of them in Florida, where he looked at the deforestation between 1900 and 1993 in Florida. saw increasing temperatures and decreasing rainfalls as a result of that deforestation. It's correlated with that deforestation, so it as a hypothesis could be attributed to it. Also in Malawi, which is the illustration on the side here, there's a 14% deforestation of the land within 1 decade, corresponding to a 9% decrease in rainfall in their measurements. So let's talk about Texas in drought and extreme weather. Here's a picture I took going through the Texas Panhandle. You see dust devils and when you're driving through the Panhandle, but very commonly, but you don't see them in forested areas very, you really don't see them in forested areas, and part of it is that the heat of the ground surface is fueling these extreme temperature things, these extreme weather things that you don't really see in forested areas. So here we're talking about the high plains, Texas Panhandle. Up above it is more of the high plains. After World War I, they were doing extensive landscape changes in the high plains. And then people pretty much figured out that later, by the 1930s, you had a really bad drought. A lot of that area changed to desert. And it was pretty obvious that it was the landscape changes that caused those changes to occur during that time. So here's about anticyclones. Nemeas wrote about this back in 1960. He said, this is why you're getting droughts in Texas. He said the droughts are really attributed to, you can correlate them more to the soil moisture in the spring before than to the heating of the Pacific oceans, which we relate to La Nina, El Nino. And he describes anticyclones as this. He said, if you've got dry soil and you're heating that surface, you've got these descending dry fronts that creating high pressure. And these are what keeps the rainfall from the Gulf coming through. And it's causing these sustained droughts in the high plains and also central Texas at the time. So if you've ever seen, the hurricanes, how they come, the hurricanes, of course, are heated up by the heating of the waters in the Gulf of Mexico, making them more intense, right? And then they come into central Texas. They're going straight line from the Caribbean, and then they come to central Texas and they start turning off to the east where the forested region in Louisiana are. So this is how Nemeas explains that that's a weather phenomena caused by the heating of the ground surface, creating these high pressure fronts. And so also there was a climate model done worldwide by Schucklin and Mintz in 1982. And they saw they did two scenarios, one of them where you have forests and one of them where you clear the forest, you don't have any soil moisture anymore. And in their model, what they saw in Central Texas, when you derive in Central Texas results, that where you had thick vegetated soil moisture, you saw much hotter temperatures in the grasslands than you do in the forested areas, which is what we saw in the other studies we just looked at. They also simulated that the rainfall in the July summertime is going to be less if you have grasslands than if you have no soil moisture, you have no forests, than if you have forested areas. So this is a model done in 1982, a worldwide climate model. And so some people tested that in the plains. They said, let's test this hypothesis like Nemeas did, and they measured the soil moisture, and they saw that that whether you had a drought there or not correlated more with the soil moisture before, which means that the soil moisture is producing moisture for the air, which could make or break whether you have a drought or not. And it didn't correlate as well with La Nina, even though nowadays you still see people using La Nina to predict whether we have a drought or not in Central Texas. But some of these studies are showing you that actually it's a local soil moisture, forest moisture, which determines whether or not you have a drought. So here's another interesting story. Texas A&M University, Brad Wilcox, noted that you had a big regrowth of forests since the 1940s. I talked about how you had the livestock and so forth. So he noted that the livestock peaked around the 1940s, and then started declining after that point. And then you had the forest regrowing after that point. And he said, well, you know, contrary to what people think about trees using up all the water, if you look at the streams, since the 1940s, the stream flow actually increased in all of these streams in Central Texas. And so he attributes that to the effect of the livestock on the land surface, affecting spring flow. You know, of course, is something we looked at before, but here's some actual data from Central Texas about that. This data didn't continue into the 2011 drought, which is the next one, to see if that trend still continues or not. But up to this point, this is an interesting finding that they've got. Here's another study locally. Brian Hunt, Raymond Slade, and Brian Smith looked locally. They said that, you know, for some reason, since 1960, the rainfall increased in the Austin area, Barton Springs increased, the spring flow increased in the area too. Now, certainly during the low flows, you know that the spring flows decline proportional to the pumpage in the area. So the thought about a wetter climate since 1960 is kind of counter the thought that climate change is causing droughts to be worse, you know, but maybe it's because it's not global climate change, but local climate change that may be causing the regrowth of the trees since 1940s and 1960, causing the flows to increase locally. So here's the conclusion. I'm going to end on this, that the Central Texas aquifers, they have little natural treatment, so they can flow surprisingly rapid, and they have surprising destinations, you know, where it may not be the closest place that's actually where it's coming out. In other words, you may be feeding springs that are 20 miles away. So cave filling was a common practice. Once restored, you can increase the recharge to the aquifer, which is always good, decrease the flooding, provide important wildlife habitat, historical records, and they also great educational resources. We can take kids underground to learn about science in there, in the public. A large portion of climate change is actually local climate change, the result of land use changes, particularly deforestation and soil loss. And the aquifers, forests, and soil, they work together to create a large water storage reservoir, what Bray said. The evaporating water flux attracts rainfall, helps to keep the droughts away. And if the forests were cleared in Central Texas, you might expect to have about 20 to 40 degrees warmer Fahrenheit during the peak summer months. Now, interesting to see, you know, what would the effect during the extreme cold, like we saw in February, you know. I suspect that would probably affect the cold too by making it less cold, but this would be something for future study. In addition to all this whole topic can certainly need more study. This is not the end. We're still learning more. We need to study this more. Forested landscapes have less runoff compared to grassland. It's pretty universally accepted. About 33 to 40% lower, which means less flooding severity downstream, possibly more local recharge, more spring flow, possibly less runoff going to the Gulf of Mexico. And the loss of the forest and soil can result in, you know, warmer temperatures and less water, less spring flow. So that's what I've been talking about this whole time. And so I'm going to end with this: go team, go. This is in Austria, where they had this exhibit and they planted these trees in the stadium. I thought that's cool. So I'm going to end on this.